Okay, so this is the second case. That's initial value problem with repeated real roots. So again, you start with this coefficient equation in R. And then once you solve it, you see that, well, let me include one more step. You see that we have a solution of 1 over 2, but it's kind of with multiplicity 2, right? So we like to think of them as, R1, 2. Both of them are 1 over 2. So this is kind of weird. Even though we only have like one value, we want to think of them as, two roots, but they are like equal to each other. But here is the important thing that you do with them. If you have like repeated real roots, the way you write down your general solution is the following. So we know general solution is like E1 plus like E2 something, right? So in the previous video, we see that when the two roots are distinct, you just put the roots as the coefficient here. So whatever t. But then since it's repeated roots, we will put an extra t for one of the exponential. And then the 2 halves still goes here. So that's kind of the only new thing in this case. And then the rest of it is kind of just computation. So for example, if you plug in 0, you get 1. So then that means C1. So now this whole term will be 0 once you plug in t equals 0. So that tells you C1 is 1. And then to use this second condition, we need to take a derivative of this whole thing, right? So y prime of t is you pull out the coefficient. And how do you differentiate this thing? I would like to maybe just use the product rule. So it's the derivative of the first term t, which is 1, times the second term, plus the first term t times the derivative of the second term, which is 1/2 e to the 1/2 t. Okay, and then you can maybe have one more step let's do that. But if you feel comfortable just plugging 0 at this step, it's okay. But I want to be like very careful here. So C2 e to the 1/2 t plus this is C2 over 2 t e to the 1/2 t. So now you can plug in t equals 0 here. So we have 1/2 C1. This is C2, right? Remember, e to the 0 is 1, so that's C2. And then this t is 0, so this whole thing goes to 0. So that's equal to 2. And from here, you can solve for C1 and C2. So C1 is 1, and then C2 is 3 over 2. And then you should make a conclusion that, now we know what's C1 and C2. So that's e to the 1/2 t plus 3 over 2 t times e to the 1/2 t. So I think the most important thing is when you have repeated real roots, then you put an extra t in front of one of the exponential in the general solution, and the rest of it is just computation. Okay. And one more thing I want to maybe include as a aside. It's not even related to this problem. So that's an aside. So let's say we have a differential equation like this. How do you write down the equation for the variable r? Be careful. It's since you only have double prime and the function itself, so it kind of means the y prime, the coefficient is 0. So then your r equation should be r squared minus 4. There's no r. It's just 4. So that's going to be the equation you're going to solve. So just, and then you will get, 2 distinct roots. So this is actually case 1, not in this case. But I just want to remind you, when you don't have a first derivative of y term, your equation should look something like this. Okay.